Hello everyone. So, in the last lecture I have just started explaining second law, and we will proceed with that, and we will see how the principles of second law that can be applied for waste heat recovery systems, and we can get different implication of second law, or rather we can have a better design of waste heat recovery system applying second law. Now, I was discussing the main attributes of second law, what is told by second law, what important information given by second law. First thing I have told, it gives us the direction of a process and it gives us the limits of conversion, how one form of energy in transit can be converted into another form. That then it gives us the concept of irreversibility. It also gives us the concept of entropy. Entropy is a very unique property. Again, most of you are familiar with the term entropy and what it is, but for the sake of continuity we will discuss little bit regarding entropy. And second law makes us aware of regarding this unique property of a system, which is so very important for any energy conversion process. Fourth, it gives or it helps us to analyze the best theoretical performance of a cycle or process. What could be the best theoretical performance limit of a cycle and process that can be analyzed by second law. Then it also gives factors that produce effects which preclude the attainment of best performance of a cycle or process. So, 4 and 5, these two 4 and 5, these two points is to be taken together. So, second law of thermodynamics not only gives us what could be the best performance of a cycle or a process, it also helps us identifying the factors which will act as impediment, which will act as obstacle, resistance for attaining this best performance. So, once you know what are the factors which is not allowing you to have the best performance out of a cycle or a process, then obviously you will try, or an engineer will try to remove this. In some cases it will be possible with the technological infrastructure we are having, with the technological knowledge we are having, to remove this obstacle. In other cases it may not be possible, but at least we know what is the best possible and we try to go close to that best possible performance of the system or the cycle. So, this is very important. Then other points what we get, this is a corollary, but again it has got great importance. It gives us a thermodynamic scale of temperature independent of material property. This thermodynamic scale of temperature, it is the absolute scale of temperature. It is of utmost importance in engineering practice, in determining the efficiency of a cycle, etc. Then next point, this is again a corollary. It also helps us to determine or evaluate thermodynamic properties. So, basically we will get certain property law using both first law and second law of thermodynamics, and with those property law we can determine other thermodynamic properties. So, that is also one contribution of second law of thermodynamics. So, with this we can see that second law gives us or contributes quite a few aspects which are utterly important, which are of utmost importance in the case of energy conversion, and obviously waste heat recovery is energy conversion process, and we have to see how this can be applied to waste heat recovery process. But before that, let me formally tell, I am not going to write it, it is available in any book of thermodynamics, but for the sake of continuity, let me state the usual statements of second law of thermodynamics, particularly for engineering practice. So, there are two statements. Again, this is known to most of the participants who are attending this subject, but for the sake of continuity it is needed, and again for those who are coming from other discipline, it is better to have some sort of a recapitulation, some sort of a re-explanation of these laws and principles, so that they can appreciate, or rather we can appreciate the later portion of this course, where time and again these laws will be applied for waste heat recovery system. So, two statements of second law. First is Kelvin-Planck statement. So, what does Kelvin-Planck statement convey to us? The statement is like this: it is impossible to construct a device which will operate in a cycle and will produce net amount of work while exchanging energy with a single reservoir or a single body. So, let us consider one engineering application, and from that engineering application let us try to understand the implication of Kelvin-Planck statement. In the conversion of energy, it is very important, because this is very common, that what we do, we burn fuel, burning the fuel we get thermal energy, and with that thermal energy we create mechanical energy or work. So, this is one conversion. So, let us say we are thinking of a conversion like this. We have got a thermal reservoir, where the reservoir is maintained at a particular temperature T1. So, this is the identity of the reservoir, the temperature T1, that is the identity of reservoir. And we have got a device which is operating in a cycle. The circle which I have drawn, that indicates a device which is operating in a cycle. So, this device which is operating in a cycle, it is taking some Q1 amount of heat from the reservoir, and let us say we try to convert this into mechanical energy or work. So, we are producing W amount of work. Now, from first law this is possible, or rather at first law is not getting violated by what I have drawn, by what I have proposed, that I will take Q1 amount of heat from the reservoir and will convert whole of it into useful work or into mechanical work. So, I am not violating first law of thermodynamics, but second law of thermodynamics says that it is not possible. If I am operating a cycle, that means if I am continuously producing work, so it will not be possible that I will take some amount of heat and convert whole of it into work when I am working or when I am operating a cycle or continuously producing work out of heat or out of thermal energy. Then what is possible? It is possible to produce continuous work if I reject certain amount of heat, and if I have to reject certain amount of heat, there would be another body to take that heat, that second body that will also be identified by its temperature. So, this is a second reservoir which is at a temperature T2 and T1 should be greater than T2. So, there can be flow of heat. While the flow of heat is there from T1 to T2, only part of the thermal energy which is flowing, that can be converted into work. So, you see the whole of thermal energy we cannot convert into work, only a part of it can be converted into work and rest of it should be dumped to a low temperature body or low temperature reservoir. Many a times the high temperature reservoir is called a source and the low temperature reservoir is called a sink. So, this is possible by Kelvin-Planck statement, this is possible, and if we think, we will find that our day to day experience, our common experience also says that. Let us think of a thermal power plant, a fossil fuel operated thermal power plant where steam is the working medium or working substance. So, in a steam power plant what do we find? So, coal is burnt, thermal energy is produced. So, we can think of, we can idealize it that as if it is a reservoir with a constant temperature. So, then with the help of that heat or at that high temperature, water will be converted into steam. The steam will be made to pass through a turbine, the turbine will rotate and produce mechanical energy. Then the steam which is at low pressure and low temperature will come out of the turbine and we will condense it. When we are condensing it, what we are doing? We are rejecting heat to the atmosphere. So, heat is taken from a high temperature source which is nothing but the burning of the fuel, and heat is being rejected to a low temperature sink which is nothing but our environment, and in between when heat is flowing from high temperature to low temperature, we are producing certain amount of work. And here you see the concept of waste heat is also coming. So, what is waste heat? The heat which we are dumping to the environment, that is your waste heat. So, in connection with the present course, whatever has been told in Kelvin-Planck statement, we have to have that but at the same time we can here in this particular case we can identify which is waste heat. So, Q2 which is called heat rejected. So, this also we can term as waste heat. Of course, there is a question that how much of it really qualifies at waste heat. That means, whether we can convert certain part of it into again some useful purpose or not. If that is possible, really that part of Q2 which can be converted into certain amount of useful I mean that which can be converted into some sort of useful energy, either in the form of mechanical energy or in the form of thermal energy. So, then we will have part of it recovered, and that is your waste heat recovery. Here we have to keep it in mind that whole of it cannot be converted into useful energy, because that then that is becoming or that is amounting to violation of second law. As first law cannot be violated, and the principle of energy conservation cannot be violated, second law also cannot be violated. So, definitely certain amount of heat has to be dumped to the low temperature sink, which is nothing but the environment here, but in many of the cases part of it can be recovered, and that is your waste heat recovery. That is all about the present course. So, another important aspect we get. So, here we get a device which is operating in a cycle, taking thermal energy from a high temperature source and dumping part of it into a low temperature sink and converting the rest of it into useful work. So, this device is called a heat engine. So, here we get the concept of a very useful engineering device which is known as heat engine. Okay. And the cycle in which it operates, that is called a heat engine cycle or a power cycle, because it is generating work or power. And well, here again we can define some other thing. You see, the energy which we are getting from a high temperature source, generally for which we have to pay, that is equal to Q1. Unfortunately, whole of Q1 cannot be converted into W, the useful work which we desire to do. Part of it only can be converted to W. So, here we can define another thing which is efficiency of the heat engine. So, let me define it. Eta, that is efficiency of the HE, that is heat engine, that is equal to whatever we get divided by whatever we have paid for. We are getting W while we are paying for Q1. So, it is W by Q1. From first law we can write it is Q1 minus Q2 by Q1, or efficiency we can write as 1 minus Q2 by Q1. So, again we get one perspective of waste heat recovery. We want to increase the efficiency of this device. If we can reduce Q2, so obviously that is a desirable situation. Now, this Q2 which is rejected to the ambient, which is dumped to the ambient, probably by adopting certain waste heat recovery principle, this Q2 can be reduced. So, that has got a direct implication, we can increase efficiency. So, well, we will see how we can have reduction of Q2, what are the different options available for reducing Q2. Then let us go to the second statement of second law of thermodynamics. First statement is Kelvin-Planck statement, second statement is known as Clausius statement. So, this statement was given by Clausius and the statement goes like this: it is impossible to create a device which will operate in a cycle and will produce no effect other than transferring heat from a low temperature body to a high temperature body. So, again let me state or let me tell Clausius statement. It is impossible to design a system which will operate in a cycle and will produce no effect other than transferring heat from a low temperature body to a high temperature body. So, what is told by Clausius statement? Let us say there are two bodies, one body is at temperature T1 and another body is at temperature T2. And we cannot have a device which will take thermal energy from the low temperature body where T1 is greater than T2 and transfer it to a high temperature body. Though by first law this is not impossible, first law does not put any barrier to this, because first law only says regarding the conservation of energy, as long as the heat which we take, the thermal energy which we take from the low temperature body, the same amount of thermal energy we dump to the high temperature body, we give to the high temperature body, this is not violating first law of thermodynamics. But second law of thermodynamics says that it is not possible. That means, the flow of heat from a low temperature body to a high temperature body, continuous flow of thermal energy from a low temperature body to a high temperature body is not possible. Again I have told that second law gives the direction of processes. So, it is also giving a direction of process. We know heat can easily transfer from a high temperature body to a low temperature body. So, that is the preferred direction of the heat transfer process, but the reverse of it is not possible, is difficult to achieve. It is achievable, but by some other means, that transfer of heat from a low temperature body to a high temperature body, it is not naturally achievable. We have to do something to achieve it. So, what we have to do? We have to give some energy or work from outside. So, if we do that, then what we will get? That we are taking Q2 amount of heat from a low temperature body, with the help of work, that is W, we are pumping in total Q1 amount of energy to the high temperature body, which is at T1. Now, this configuration, it neither violates first law, because we know from energy balance Q2 plus W is equal to Q1. So, energy conservation principle is satisfied, and it is also satisfying Clausius statement of second law of thermodynamics, that heat cannot automatically flow continuously from a low temperature body to a high temperature body. We have to have some assisting device for this kind of flow, and as assisting device we are having the work supply from outside. So, this is again another important device, another important engineering device. In fact, it talks about two important engineering devices. So, these engineering devices are called heat pump and refrigerator. So, a refrigerator creates low temperature. So, what we can do, what we can see from this example that we are taking heat from a low temperature body which is at T2. So, it is helping us to maintain that low temperature. So, basically then it is helping, I mean the device which I have drawn, that is showing a refrigerator, where by putting external energy I am continuously extracting heat from a low temperature body. So, this acts as a refrigerator, and when I am calling it a refrigerator, my focus is at the low temperature body and at the heat or thermal energy which I am extracting from the low temperature body. But at the same time I can have a different outlook also. So, this can also be called a heat pump, because as by a pump we pump water from a low level to a high level, here also by this device and providing certain amount of energy input in the form of work from outside, I am pumping heat from a low temperature body to a high temperature body. From T2 to T1 I am pumping heat. So, this is also called a heat pump, and in that case our focus is the high temperature end of this example. That means, our focus is at T1 and the heat supplied to it, that is Q1. So, this is Clausius statement, as Kelvin-Planck statement gave us a very important engineering device called heat engine. Here also we are getting an important engineering device. Depending on my choice, my preference of working of this device, I can call it either a refrigerator or a heat pump. So, I will start from this point in the next lecture.